Okay, so I'm going to say more about these thing called the states. Um, okay, and states are more or less synonymous with the word eigenstate, and I hope you are more or less familiar with this notion of an eigenstate. For example, in the case of an hydrogen atom, there are all these levels: 1s, 2s, 2p, etc. These are all different labels representing different eigenstates. Okay, and in principle, there are infinitely many or infinitely different eigenstates for the electron for an electron to occupy in the case of an hydrogen atom. So there's a usually a huge variety of eigenstates for a particle to go into. But actually, there's a huge simplification taking place in the case of quantum systems that we use for quantum information and quantum computing purposes. Um, Most often, we are focusing ourselves to situations where there are only two relevant levels or two relevant states. Okay, so these two different levels are, for the sake of convenience, are denoted as a 0 and 1. And in real life, this zero state can be, for example, the spin of some particle being up, and the 1 can be the same spin but pointing down. And but I should emphasize that these two different states, 0 and 1, they don't really have to correspond to any physical spins. Okay. Maybe this example will help. For example, let's say I have this some sort of double well potential, so that an electron or some particle in general can have a high probability of being in this left potential minimum or the right potential minimum. And if the particle happens to be located on the left potential well, then we say that the electron is occupying the state 0. And in this case, we say that the electron is occupying the state 1. Okay, so in this case, the 0 and 1 have nothing to do with the spin, but rather have to do with the simply two different choices of a quantum state for a particle to exist in. And the other condition that we often impose, almost without exception, to such a two-level system is that these two levels have the same energy. Okay, so the energy of these level 0 is assumed to be identical to the energy of these other level. Okay, and such a situation is described to be a degenerate, and this is a word that people use a lot in quantum mechanics to refer to more than one eigenstate having the same energy. Okay, so why focus only on two level systems? Well, the reason is more or less pragmatic. I think it's the same reason as as why we only tend to fabricate classical computers out of bits. Okay, bits are basically they are ways of encoding information in terms of either 0 or 1. But then there's nothing absolute about this binary system that we adopt to represent information. Instead of bits, we could have chosen to encode information in terms of these three different states, 0, 1, and 2. Okay, so if we had done that, then the information string would be like this: 0, 1, 2, 1, 0, 2, etc. Okay, so any string of such numbers would correspond to some sort of information. But instead, since we are adopting the binary system of representing the information, the information sequence would be written like this. Like this, okay? But I emphasize that there's nothing absolute about this way of encoding information. One could easily have encoded information in this way and still have made a perfectly respectable computer. But it would have been a lot harder to actually come up with a hardware that can process information in this manner, because then what one has to do is to be able to place a given physical system into one of these three possibilities in a very, very precisely controlled manner. And it's already hard enough to do that with only two possible choices for a state, namely either 0 or 1. And having another state to have a control over would be a huge challenge to to the engineers who try to come up with a physical realization of this information science. Okay, so I think for that reason, people have stuck to the simplest possible scheme, which is to represent information in terms of these binary system. And in quantum mechanics, or in the case of quantum computer, the situation is more or less the same. Although we have an extra feature called the superposition, okay, which I will get to in a short while. Superposition. But a superposition is also founded upon having a certain number of basis states. Okay, so here's another keyword that will come into play and play an important role, namely the notion of basis state. And if we only have two of these states to use as a basis, then in general, any given quantum state would be a linear superposition of these two states in this manner, where again these two coefficients are some complex numbers. But now instead of bits, we have let's say we had a 3-level system. Okay, so let's add another level or another basis called 2, which would then involve the use of a third coefficient, gamma, which is also a complex number, and the ability to have a control over these quantum states represented using these three basis states would require that we somehow maintain a precise control over not just two, but three different complex numbers at all times. And I guess anyone who has raised children or puppies would know that raising three is much harder than raising two. Whether these two being either human beings or puppies. So there's a similar challenge for having a precise control of these quantum states. The more bases you have, the harder it is to have a precise control. And of course, if you have only one basis, let's say only this basis, then it's the most boring system in the world, because once a particle is in this state, then it has always to be in that state because there is no other state for the particle to go into. So that won't be of much help in constructing a useful information processor. So the minimum number of bases you would have to introduce is two. Okay, so the qubit is nothing but a reference to a state which is a general superposition of two different basis states with this extra condition being that these basis states share the same energy. Okay, and the reason why this extra condition is useful is because if their energies are the same, then the transition between 0 and 1 is going to be easy. Okay, and that will facilitate the construction of a quantum computer based on the bit qubits as an elementary unit. Okay, so so then this is why I want to basically reconstruct quantum mechanics in terms of two-level system. So another way of saying it is that I want to revisit the entire formulation of quantum mechanics, pretending that these quantum mechanics only works on a system consisting of two basis states, or in other words, the quantum mechanics only applies to a two-level system. And the reason that such consideration is sufficient for our purpose is, again, due to the fact that in the construction of a quantum computer, a two-level system is the most useful and efficient platform for making a quantum manipulation of the state. Okay. So how do we write down the quantum mechanics of two-level system? And so in other words, what is the Schrodinger equation of a two-level system? And of course, there's a following question is, what is the solution of such a two-level Schrodinger equation? Okay, and the important caveat is that this is a Schrodinger equation for a two-level system. So that lecture will be coming in my next video.